Now, for a collection of particles with the same mass at a given temperature, okay, we can show the following. Okay, first of all, translation kinetic energy we say is k 1/2 times the mass times the square of the speed, right? And we've already shown that the average translational kinetic energy is 3/2 kT, where k is Boltzmann's constant. So if you have a collection of these particles, okay, then your 3/2 kT would be equal to 1/2 times mass times the average of the square of the speed. Why is that? Let's see. If we say the average kinetic energy is 3/2 kT, right? Case of dt. That is 1/2 mv1 squared plus 1/2 mv2 squared plus 1/2 mv3 squared, and so on, right? Divided by the total number of molecules. Well, this is going to be 1/2. I can factor 1/2 m. They all have the same mass. v1 squared plus v2 squared plus v3 squared, and so on, divided by the total number of molecules. So that is just going to be equal to 1/2 times the mass times the average of the v squared, the average of the square of the speeds. Okay? So you add up all the squares of the speeds divided by the number of molecules. That gives you the average of the square of the speed. All right. So the average of the square of the speed, then, you can solve for that, is 3/2 kT divided by 1/2 m, right? So what would that be? This is going to be 3/2 kT divided by 1/2 m. So you can see your 2 cancels out. So that just gives you 3 kT divided by m. And kT, if you recall, is just r divided by Boltzmann's constant, if you recall, is just r divided by Avogadro's number. And the mass of one molecule is the mass of 1 mole. So big M sub m here is just the molar mass. Okay, it's molar mass. So if you take the molar mass divided by the Avogadro's number, that gives you the mass of one molecule. So this little m right here, the mass of one molecule, is the mass of 1 mole divided by Avogadro's number. So if you make that substitution, what do we see? Avogadro's number cancels out, right? So the average of the square of the speed is just 3RT divided by the molar mass. Okay? So from this, we can take the square root. We take the square root of this. So that's the square root of the average of the square of the speeds. You get what is known as the root mean square speed. So it's going to be equal to square root of 3r, square root of this thing right here. So square root of 3RT over the molar mass. So that's called your root mean square speed, RMS. Okay? Root of the mean of the square. The mean of the squares is the average of the squares, and root means you take the square root of it. So the RMS speed, as you can see, is directly proportional to, okay, the square root of the temperature, okay, and inversely proportional to the square root of the molar mass. That means the higher the temperature, the higher the average speed. You can think of RMS speed as sort of like an average speed. Okay, it's not really a true average speed. It's the square root of the average of the square of the speeds. Okay, but still, it's going to be related to the average speed. It's the higher that value is, the higher the average speed is. So that we can say the average speed. Let me just think of it as average speed for now. Is directly proportional to the square root of the temperature. So the higher the temperature, the higher the average speed. The higher the molar mass, the heavier the molecules are. Okay, you have an inverse relationship here. This one's in the denominator. The higher the molar mass, the lower, for the same temperature, the lower the average speed. Okay, so that's what that equation means. So like I said, RMS speed is sort of like an average speed. The true average speed is actually just slightly smaller than this, but it can also be shown to be directly proportional to the square root of the temperature and inversely proportional to the square root of the molar mass. In fact, so if this is the formula for the root mean square speed, you can actually show, and we're not going to do it at this level, but in higher level class, you'll show physical chemistry, you can show that the average speed is equal to 8 RT over pi times the molar mass. And 8 over pi is just 2.5465. Okay. So let's apply those ideas to this question. Which gas sample has particles with the slowest average speed? Is it 2 moles of helium at 298 Kelvin, 1 mole of helium at 500 Kelvin, or 2 moles of O2 at 298 Kelvin? So what's our formula for average speed? It's inversely proportional to, it's directly proportional to the square root of temperature, inversely proportional to the square root of the molar mass. Okay, let's write molar mass this way, m sub m. So let's compare then temperatures. Okay, so notice that you really don't, it doesn't matter how much you have. Again, anytime you're comparing averages, it doesn't matter how much you have. So temperature 298 Kelvin versus 298 Kelvin, helium versus O2. So let's compare A and C. Which one has a bigger molar mass? Molar mass O2 is larger than helium, right? So you've got a bigger denominator for O2. So the heavier oxygen molecules would have what? Would be more sluggish, you'd say. It would be smaller for larger molar mass. So it would be slower for O2. Okay, so O2 would be slower than helium, so you can cross this one out. Okay. What about helium? O2 at 500K versus O2 at 500K. Okay, you've got different molar masses, different temperatures. You can't make a direct comparison. So let's compare A and B instead. What happens between A and B? So we've already compared A and C, right? And we said it can't be A. Let's compare A and B then. Well, let's see. We're comparing helium. Again, doesn't matter how much you have. So helium at 298 Kelvin versus helium at 500 Kelvin. So which one has a higher speed? Higher temperature, higher average speed. So we say helium would have a higher speed. Okay, so at 500K than 298K, so it can't be B either. So the correct answer here is oxygen at 298 Kelvin. Okay, so summarize. Compare these two, the lower temperature would have a lower speed. Compare these two, the heavier mass would have a lower speed. So the answer is C. Let's actually calculate the average speed of O2 molecules at 298 Kelvin. So the average speed, square root of 8 RT over pi times the molar mass. Let's do this calculation because you have to, I want to give this specific example because I want to show you how the units work out, okay? So this is going to be equal to 8 times. The best way to do this is put everything in the base SI units, so 8.314 joules per Kelvin per mole, and our temperature is 298 Kelvin, divided by pi, which is no unit. Molar mass of O2 is 32 grams per mole. Okay, but you have to put that in kilograms. Okay, so 32.00 times, so let's put that in grams first, grams per mole. But you have to change your grams to kilograms, so there's 1 kilogram in 1,000 grams. So grams cancels out. Moles cancel out. Let's look at the unit inside, okay? Kelvin cancels out. So what's the remaining unit? The remaining unit inside your square root sign is joules per kilogram. What's a joule per kilogram? A joule is a Newton meter, right? Force times distance is joules over a kilogram. A Newton is a unit of force. So force is mass times acceleration. So that would be a kilogram. Acceleration is meters per second. So meters per second squared. That's a Newton, okay? And times a meter over kilograms. Your kilogram cancels out. So what do you have left inside in terms of base units? The unit inside is going to be meters squared per second squared. And if you take the square root of that, okay, the unit that comes out will be meters per second. So let's plug in all these numbers. 8 times 8.314 times 298 divided by pi divided by 32 and divided by 1 over 1,000, so you multiply by 1,000 times 1,000, and that gives you 1.97 times 10 to the 5th, and then take the square root of that, so inverse, oops, I don't have a square root thing here, so I'm going to raise it to the power 0.5, that makes it a square root, equals, that's 4.44 times 10 to the 2. So in regular notation, that's 444. Okay? So this is 444 meters per second. That's the average speed of oxygen molecules at room temperature.